Welcome to your first unit of statistics. In this unit, we begin our journey in how to turn data into information. When you look at a sample of raw data, your vision might blur from all the numbers that say nothing, even though they're organized neatly into columns with headings in the first row. But until you start to group the data and look for patterns, it's meaningless. So here you'll learn to analyze data through tables, graphs, and descriptive statistics. We use tables and graphs to align data by some common themes and either display the information in a simple picture, like a pie chart or a bar chart, or in a table in which we can read the subtotals that comprise the pie slices or the bars, like in a frequency distribution. When we wish to present a single number to describe some aspect of the entire data set, we use descriptive statistics. For example, the average, also known as the mean. Considering that so many government reports and business presentations use tables and graphs, sometimes with misleading information, and yet presented truthfully, and since we live in a society that's obsessed by basic descriptive statistics like mean, median, and mode, and are not afraid to use the one that best suits the argument in question, it behooves us all to learn to read and speak this seemingly foreign language. But you'll speak it like a native in no time. And incidentally, if you find yourself saying, "It's all Greek to me," don't be surprised, since many of the statistical terms use Greek letters as their symbols.
Let me start off by asking, what is statistics? Well, you probably hear that term thrown around all over the place when you associate it with sports, weather, politics, of course. Polling is done so often. But statistics is really a compilation of tools and techniques that we use to analyze data. There's all kinds of tools available to us, whether it be charts and graphs or calculations or whatnot. But these are tools that enable us, as I pointed out, to turn data into information. Some of it is very personal. You know, a lot of people can look at the same charts and see something different. I bet if I had 10 people look at the exact same graph, I would get 10 different interpretations. And that's okay that people have slightly different interpretations as long as their interpretations are grounded in the graphs that they see. So this course is really about learning how to take that data, learn to take those charts and actually say, what do I see in there? In the business world, there's a lot of uses for statistics. We sometimes just want to get a summary of what's there so we can make decisions. Sometimes we just want to draw conclusions. A major use of it is for forecasting. Lord knows in the world of finance, we're always trying to predict where's our money going to go, what's going to happen, and there's so many financial ratios out there that people analyze to try to figure out whether they should buy or sell stocks. And then ultimately, you're trying to make business decisions. And that's why statistics is so important in a business program, because we need to make decisions, and the decisions should be grounded in data. So why do we learn statistics? Well, it'd be nice if everyone could be a doer of statistics. But that's a lot to hope for. Beyond statistics majors, and then some of you who truly aspire to be super analysts, the aim here is really to make you more of a super user of statistics, not a casual user. I don't like the idea that people just blindly trust headlines that they see without any substance. You don't know where the facts come from. You need to be able to see through the data and ask the right questions. But you don't know what questions to ask if you are not at least somewhat intelligent about the subject matter. So by making you an educated user of statistics, you will know what the good questions are to ask and what you should believe and not believe, and who you should trust and not trust. Statistics can be broken down many different ways. One way is we can say there's two branches of statistics, descriptive and inferential. In the first part of the course, we're going to cover descriptive statistics, which, just like the name implies, means we're describing. So we have a set of data, and I say, what does that data tell you? And you basically will slice and dice that data every which way, draw graphs, make tables, and tell me what you see. Inferential statistics, which we cover in the second half of the course, that's about taking the data from a small data set, basically, and inferring what it probably would look like if you had looked at the whole. Think of all the polling that's done. They don't survey every living, breathing voter. For one thing, it would cost way too much money and take way too long. So they survey a group of people, we call it a sample, and then from the results of that, they infer what they think everybody would have said had they asked everybody. So we look at these polling numbers and we get an idea of who's ahead and who's behind. But that's the essence of inferential statistics, where you take data and infer to the whole from the small. Let's address some basic terminology. Variables. Now this one seems to get misused a lot. If you think about the word variable, it's vary and able. Something that is able to vary. So for something to be a variable, it's got to have a range of values. Gender is a variable because it can have the value of male or female. Heights, weights, ages, whatever, they're variables because there's multiple values for it. But you wouldn't call female a variable. Female is a value of a variable. It's one possible value of the variable gender. So you got to be clear about that, because when in our analysis we're always discussing variables, and if there's only one possible value, there's not much analysis left to do, so variables must have at least two possible values to truly be a variable. The simplest piece of data, we call it an observation. Now, I know the word observation has kind of a strange name. Why don't we just call it a data point? And it is called that in many books. But it's called an observation because it really had its origins in the social sciences. We watch the lab rat going through the maze, and we observe how long it took to get done and how long it took to accomplish its task, and we record the time. So a lot of the data that was recorded was based on observations, so the name stuck. Statistics, by the way, is not a math course. It is a social science, as you'll see throughout. This is not a course about how to do math. It's a course about understanding data. You'll find many courses, economics, finance, and accounting, or whatever, that have a lot more math than statistics does. So this truly is a social science. Go back to observation. If you have all possible observations put together, you have what we now call a population. Now the word population, if you look at its Greek origins, implies people. But it doesn't have to be people. We can have the population of all books in a library. It's not people. It's still a population. As long as it's all possible observations that could belong to the data set, it's a population. Any subset of that population is called a sample. A sample doesn't have to be of a certain size. You could literally sample the entire population. You could sample 99% of the population. Then again, you can sample 1 or 2. So samples can have any range of sizes to it, but it's a subset of a population. And once again, going back to inferential statistics, we're using a sample to infer what's true about a population. So we take our data from our sample, we crunch the numbers, we do analysis, we actually call that number crunch, whatever we compute from a sample, we call a statistic. Whatever we compute from a population, we call a parameter. So think of it this way, population, parameter, both begin with a P, sample, statistic, both begin with an S. So we actually use statistics to draw inferences about populations. Well, this entire course is called statistics, not parameters. For good reason. We rarely, if ever, analyze populations. You know, it's not something that we often have access to. It's not very practical to be analyzing entire populations. Sometimes it's impossible to try to get the data for an entire population. Heck, do you really trust most censuses these days? Do you really believe they've got every living, breathing human being captured? It's highly unlikely. So we focus on analyzing samples. And so the analysis of a sample yields statistics. So that's why the course is statistics. It really is about analyzing samples and using that data to either just describe the sample in front of you or to draw inferences about a population. Now let's go back to variables. When we describe variables, we can classify them many ways. One breakdown is to compare variables as either being categorical or being numerical. Well, categorical variables, essentially, it's qualitative, essentially non-numerical values like yes or no, boy or girl, what color hair a person has, what's the political party of the person, does he wear glasses or not. So you can see it's a grouping variable, and there can be many categories. There could be a limited number of categories. While a numerical variable is generally quantitative in nature, the values are measurements. And within the numerical world, we have another subcategory. We can call variables discrete or continuous. A discrete variable, think of it as finite, countable, where the values are separated, such as number of children. You really don't see a household with 2.73 children like you hear about all the time. You would distinctly have 0, 1, 2, 3, etc. Or number of books on a shelf, number of cars in a garage. They are discrete variables. They're finite integers. Continuous variables, well, that's where you get into decimals. The value could be any value along a continuum, along a range. Like, is anybody really 6 feet tall? That means the person has to be 6 feet, 0.00000 inches exactly. You may never in your lifetime meet someone who's exactly that. But when we say a person's 6 feet tall, really we're saying their height is somewhere between 5'11" and 3/4 and 6 foot and 1/4 inches, because we round heights off to the nearest half inch. That's about as accurate as we can get it. So we don't know, but we say that it's 6 foot, but really they're in a range. And if we wanted to group people, we would typically take continuous data and group them and say, well, we're going to get people who are making salaries of $40,000 to $50,000, $50,000 to $60,000. You're not likely to say, I want all people who make $50,273.16. You wouldn't do that. So with continuous data, we tend to group in ranges, while discrete data, it's pretty much taken care of by itself because they are integers. Now, before we really set on to analyze our data, we have to know what kind of data we have in front of us. So what we basically want to know is, what is the level of measurement of the variables? There's 4 levels of measurement. From the lowest to the highest, we call them nominal, ordinal, interval, and ratio. Nominal, which is the most basic, it's categorical. The word nom comes from Latin. It means name. So it's really a naming variable. You are male or you are female. You have black hair, you have red hair, you have blonde hair, you are Republican, you are Democrat, etc. It's a categorical variable that names. It can have numbers in it too. Basically, it's data that you would never average. The data is such that the numbers in there do not really have a numerical meaning where that you would ever do any real analysis on them as numbers. For example, zip codes. You're not going to turn around and say, my zip code is bigger than yours, or what's the average zip code in the class so we can get an idea of where the typical student lives. That wouldn't make a whole lot of sense. A zip code truly is a nominal variable, and it has categorical analysis written all over it when you think about it. Because if you look at the zip code, the first digit tells you whether or not you're in the southeast, northeast, and so on. The second digit will tell you what state you're in within that region. The third digit will tell you what part of the state you're in, and the fourth and the fifth will tell you what part of that city you're in. So it actually does tell you categorical information, even though it's a number. Likewise, Social Security numbers and phone numbers. You would never draw comparisons of one number to another number. The number has meaning, but not in terms of what's greater than what. Ordinal data is the next level up. Ordinal data, think of order. It's got an order of merit. We know it's got a ranking to it, which says this one is greater than this is greater than this. But the scales are not consistent. You would never turn around and average it. You know that one is greater than another, but you don't know by how much. The person who crossed the finish line first beat the person who crossed in second, who beat the one who crossed in third. But one might have edged the other one out by a second, and then the next one might have beaten the person by 2 minutes. So the gaps are all over the place, but we know the order is there. When you think about all the surveys that people do, or people say on a scale of 0 to 10, how would you rate blah, blah, blah? Well, we know that something that you give a 10 to is better than something you give a 9 to, which is better than an 8, etc., etc. But by how much? Because you might be the kind of person that says, I'll give any waitress 5 out of 10 if she'll actually refill my water glass once. getting an 8 requires my meal be really good, 9 being like the best meal I ever had in my life, and 10, I could die a happy man today if it was a 10. So your scale is not what I would call very evenly spread out. That sounds more like a Richter scale for earthquakes. It's all over the place. But yet it is ordinal, because your 10 is better than your 9, which is better than your 8, etc. So, but you just would never average that kind of data. Likewise with the famous Likert scale, where people rate something as strongly agree, strongly disagree, or very satisfied all the way down to very dissatisfied. People will often use a 5-point scale, sometimes 7 points, and we know that a person's 5 is better than a 4, which is better than a 3. But by how much? It might not take a lot for you to agree with some statement, but it might take a heck of a lot for you to strongly agree with it. So it's a little bit to get you to be positive and a lot to get you to be very positive. Hardly the kind of data you would average, but it definitely is ordinal in nature. And by knowing it's ordinal, there's certain analysis tools we can use on it that we cannot use on nominal data, because we have more to work with. The next level up we call interval, and the last level is ratio. And I'm mentioning these two together because of the fact that there's so much overlap there. Interval has consistent intervals. So like dollars and weights and heights and whatever, a dollar is a dollar, an inch is an inch, a pound is a pound, etc. We have a consistent interval. Because of that, we're able to do averaging. The difference between interval and ratio is only one minor piece of information, and that is that 0 on the scale must mean the absence of. If 0 means what you would think 0 means, you can actually make ratio comparisons. Like 0 pounds means weightless. 0 inches means heightless or depthless. And because of that, we can make a comparison and say that 100 pounds is twice as much as 50 pounds, and 4 times as much as 25 pounds, and 6 feet is twice as tall as 3 feet, and 3 times as tall as 2 feet, etc. We can make ratio comparisons because 0 means 0. But if we were looking at golf scores, well, if you just count total strokes, 100 strokes is twice as many strokes as 50 strokes. But when we start adjusting it for par, and a person is 2 over par because they took 73 strokes, and someone else was 1 over par because they got 72 strokes, you're not going to say that the person who had 2 over par did twice as badly as someone who did 1 over par. They did 1 stroke worse, and a stroke is a stroke is a stroke, but you're not going to make a ratio comparison, and the reason why it doesn't work is because a score of 0 is not the absence of strokes. It's just a number on the line. This would also work for temperature. When we use degrees Celsius or degrees Fahrenheit, 0 degrees is not the absence of heat, so 100 degrees Fahrenheit is not twice as hot as 50 degrees, but it is 50 degrees hotter, and a degree is a degree is a degree. Only if we use the Kelvin scale, where 0 degrees is truly the absence of heat, it's absolute 0, then you can say, 10 degrees is twice as much heat as 5 degrees. So we can average temperature, we just can't make ratio comparisons. But truly, we don't care, because virtually every statistical tool that you can do with ratio data, you can do with interval data. For our purposes anyway. The only thing out there that you can do with ratio that you can't do with interval data is something called a geometric mean. And in all my years of teaching statistics and doing statistics as a user, do, or whatnot, I've never had to do a geometric mean outside of the course I took in which it was covered. So it doesn't seem like it's something that you will likely ever have to do. So for our purposes, we're going to merge interval and ratio together, and we'll just call it scale data, because they have consistent scales, and it opens up the door to pretty much all the other analysis tools. You can also say it's interval/ratio if you wish, but basically we're going to treat them as one type of variable. Now let's look at the analysis tools themselves. Let's start with the simplest data where we're really limited, the nominal data, the categorical data basically, where there's not much we can do there except for a categorical data analysis. And we have an Excel file called Categorical Data Analysis that's available for you to actually conduct simple, basic categorical analysis. It pretty much covers the scope of what you can actually do with it. Your graphing is rather limited to bar charts and pie charts, because basically all you're doing is counting. You're not averaging. Well, if you take a look at this particular chart, you'll see that I've got 25 values, 25 observations in a data set showing class years. They could have been put in any order. It doesn't matter. You do not need to sort the data. It doesn't hurt. It doesn't help. It doesn't do anything. So I've got 25 classified as freshman, sophomore, junior, and senior. On the left side, I've got room there for up to 200 observations. You could literally go on and on and on. I just limited it for educational purposes. On the right side, you put in what the possible values are, and the table will then count. Now, all the Excel tools in this course are set up so that the yellowish or off-yellow boxes are ones where you can load information, and the ones that are bluish, sometimes greenish, are ones where information's coming out. So, data goes into the yellowish ones, and information, output, whatever, comes out in the bluish-green ones. Typically, it's yellow and blue. So after the data is loaded on the left side, when you go to the right side, we see the actual frequency table. You load the possible values in. In this case, the only values are freshman, sophomore, junior, and senior. You can put it in any order you want, but realize the order you put it in is the order that it's going to show up on the charts that we've created, and you can go back and change them if you wish. So I've loaded those 4 values in there. You don't want to leave any out. If you leave something out, there will be an error message that will display to tell you you haven't included them all. So you have to make sure that you've accounted for all 25 in the sample. The frequencies are telling us how frequent or how often something is actually occurring. So a frequency of 4 for freshmen tells us there's 4 freshmen. There are 5 sophomores, 7 juniors, 9 seniors. So in the total, add those up, you'll get 25, which incidentally is the sample size. If you held your mouse up to any of the cells where you see that little red triangle, it actually gives a description of what's in those boxes. So for example, if you held the mouse up to the little red triangle next to the word values, a box will pop up that says, enter the unique values that appear in the data so they can be tabulated. Do not omit any of them. And there's instructions for several of these. So anytime in any of the spreadsheets you see a little red triangle, go ahead and move your mouse over there to see what information there is, because it will help you to understand that particular concept if you have any questions. The last column in the frequency table is called relative frequency. It's called relative because it means relative to the rest of the sample, how big is this? Because to just say there's 4 freshmen in my class, well, I may have a class of 5, which means that my class is dominated by freshmen. I may have a class of 50, in which case freshmen hardly even appear in my class. So relatively speaking, is that a lot or a little? You wouldn't know that by just the frequency. But 4 students out of 25 is 16%. So now I can actually say 16% of my class is freshmen, 20% are sophomores, etc. Now that data has a lot more meaning. So by actually dividing it by the sample size and computing the percent, that relative frequency tells us a little bit more information than just the raw frequency tells us. If you click on the Charts tab at the bottom of the screen, you'll now actually go to a separate page which feeds off of the data you loaded. These charts are live. So that means as you change the data, these charts will change. So if you decided to add more data or change the order of your values, freshman, sophomore, junior, seniors, these charts will automatically change. There's no reason you would have to actually edit these unless you just felt like changing the title, changing the colors, or whatever. You wouldn't have to do much. And you notice here on the left side, I've created a bar chart. And it's in the order as entered, freshman, then sophomore, then junior, then senior. And it's using the relative frequencies, so you can see the 16% freshmen, the 20% sophomores, etc. You might decide that you want to do it in order from largest to smallest. That's fine. I could have set this up to do this in an automated way, but it would have been far more complicated, and it's a lot easier to make it so that you can manipulate it the way you want, so you have complete freedom versus it being locked into being largest to smallest and no other choice. On the right side, it's a pie chart, and then it's going to be in a circle, so regardless of what order you type it in, it's basically going to be the first one's going to be in the upper right, and it's kind of working its way around in a circle. And it's got 10 bullets there. That's because I set it up so there's the potential for 10 possible categories or values, and there's no way for me to program this to just to ignore those. So you see a few zeros in there, which are really easy to ignore. As you add another group, it would just add another slice of the pie to it, and it made every pie piece into a different color, so they really stand out, and the actual relative frequency value is embedded in the pie slice. So it's very easy to read these. These two charts represent pretty much the scope of everything you can expect to get out of categorical data, but still useful. You can't really do a whole lot more with it beyond this as far as graphing it, but these two do tell quite a picture anyway. And for some people, it's plenty. You know, I know there's variations on pie charts, bar charts. People like their 3D graphs, their overlapping values, whether the bars stand out or not. I mean, you can get fancy with it, but essentially this is about as deep as you're going to get. So we've seen what we can do with categorical data, and that works well when you have data that's either categorical, nominal, whatever, or even discrete variables. You could use that particular tool for numerical data that's discrete. Like if you just said, well, everybody in the class told me that they either have 0 children, 1 child, 2 children, 3 children, 4 children, and that's about it. Since you have such a limited range of values, you could certainly use it. Or how many courses are all my students taking? Well, I don't know of any students of mine that are taking more than 5 or 6 classes, so you'd have numbers ranging from 1 to 6. Once again, as long as it's a limited number of values, you could certainly use it to analyze discrete data that is numerical. But of course, realize this tool is not going to compute averages and stuff, but that still, you're going to get an extra chart or two that you're not going to get from some of these other applications. Now let's move on. What if our data happens to be of the continuous kind? When we're starting to analyze things like heights and weights and ages and GPAs and salaries and whatnot, well, it can get ugly, because you're not going to say how many people have exactly this salary, exactly that salary, or exactly that age. You'd be going crazy if you had a bar for everyone who's exactly 39, exactly 40, exactly 41. You'd have way, way too many bars, and a lot of bars with zeros and ones on it, and a pie with a lot of slivers on it. Not very helpful for analysis purposes. So for that, we've created something called a frequency distribution. With a frequency distribution, as you can see in this Excel file, you load the data on the left side. Once again, you can load a couple of hundred individual pieces of data. Doesn't matter what order you type them in. Then to the right of it, we have our frequency table. Whereas in the categorical, you just named the category and it told us how many. Here, you're putting in ranges. Make sure you include whatever the lowest value and the highest value are in the data sets. You don't want to leave any out. So we know the lowest data point, observation in this case, is 1.59 by looking at it. So I decided to make my very first lower limit 1.5. We like to use round numbers. People start wondering, why did you start with 1.572 or some oddball number? So it's nice. Even censuses, they'll count people's ages by grouping them in the 10s digits or the 5s digits. So it's like 20 to 25 or 25 to 35 or whatever. So they like numbers ending in 0s and 5s. Here, I decided for GPAs, I'm grouping them as in half-point increments. So going as low as 1.5 all the way up to 4. Notice also that there's a less than or equal to symbol next to the lower limit, but just a less than symbol next to the upper limit. That first range includes anyone whose GPA is as low as 1.5, but up to, but not including 2.0. So if it's 1.99999, it goes in that row. If it's 2.0, it goes in the next row. So where one row stops, the next row starts. There is no overlap. There is no gap. It immediately starts in the next row. So it makes it a lot cleaner for analysis purposes. The column called frequency is telling us how many of the observations are in that range. Well, the data is not sorted, but if it were, you could see that 4 of the GPAs are less than 2.0, but at least 1.5. 8 of them are between 2 and 2.5, etc. And the sample includes 25 total people. So the frequency is just what frequency is from Categorical. It's how many of the values are occurring in that range. The relative frequency is saying percentage-wise how large is that particular group. So we have 4 people that have between 1.5 and 2.0 GPAs. Is that a lot? It's 4 out of 25. 4 out of 25 is 16%. Below it, 8 out of 25 is 32%, etc. Until we've accounted for the entire 25 students and the entire 100%. So the relative frequency has the exact same meaning as before. The cumulative frequency column, think of the word accumulate, because essentially that's what's happening is it's accumulating as it goes down. There are 4 people in the 1.5 to 2.0 range. The next range has 8 people. Well, 4 plus 8 equals 12. So you'll notice the cumulative frequency for that second row is 12. What that means is that there are 12 students whose GPA is less than 2.5. So, because I've already accounted for the prior row and that row combined, I don't have to say the range anymore. I can just say there are 12 people who are less than 2.5 because it accounts for that range and all ranges prior to it. There are 18 people whose GPA is less than 3.0, 4 plus 8 plus 6, etc. And the cumulative relative frequency kind of combines the cumulative and the relative. There's 2 ways to actually look at this. You can actually look at the cumulative frequency and say, well, there are 18 people whose GPA is less than 3.0. How big is that? Well, 18 out of 25 is 72%. 22 out of 25 is 88%, and so on. So I'm actually saying that 72% of the students have a GPA less than 3.0. That 88% have a GPA less than 3.5. So I essentially took the cumulative frequencies and converted them into relative frequencies by computing the percentages. You could do it a different way if you had to do it manually. You could start with the relative frequencies and add them up. 16% plus 32% equals 48%, which is the value in the second row. 16 plus 32 plus 24 is 72%, which is the value in the next row. So you can either take the relative frequencies and add them up, accumulate them, or you can take the cumulative frequencies and compute the relative frequencies of them. Either way, you get the same thing, and we call that the cumulative relative frequency. And it does have merit to say 88% are below this, 72% are below this, and so on. So we took this simple data set, and based on the way we grouped it, we have 4 different ways to read that data. Below it, we have a graph that's known as a histogram. Now you might say, but isn't it just a bar graph? Actually, it's a special kind of bar graph. A bar graph for categorical data has gaps in it because they're distinct values. You don't put the bars next to each other. You know, a person is clearly male, clearly female, clearly blonde-haired, clearly brunette, clearly redhead, etc. So the bars are distinct and the bars have gaps from each other. Here, where one bar stops, the next bar starts. Because if a person is in the first group, they're up 2 but not including a 2.0, the next bar starts right at 2.0. So that's why they should be contiguous. And so the bars do touch each other for that very reason. If they touch each other, it's a histogram. If they don't, it's just a straight old bar graph. I used the relative frequencies in this case, so you can see on the graph that there's 16% in the first group, 32% in the second group, and so on. And you can see the way the data happens to flow, how it happens to look. Below the graph, it actually labels each bar based on the lower and upper limits that you use. So in this case, you can see the 1.5-2, the 2-2.5, and so on. If you change the upper and lower limits, it changes the labels on the bars, and of course the values are going to change that go along with it. Now you can actually get a completely different picture if you mess with this, with the intervals. You know, they say a picture paints 1,000 words, and boy, can you ever distort that picture. One of the things I always like to emphasize to people is that, you know, you really have to have some kind of sense of statistical purity when you do analysis. You know, my intent is never to deceive, but to unveil. and disclose, so people can see the truth. They can draw their own conclusions to some extent, but they need to see the truth. I always require that people make the intervals the same size, if at all possible. I do make exceptions, but generally speaking, the intervals should be the same size. You'll notice all the intervals here are half a grade point. I make the exception only on the two intervals at the ends. Like if you were doing analysis on people's ages, you might say, well, make the first interval 15 to 25, 25 to 35, and 35 to 45, and so on. And let's suppose that out of 100 people, that 99 of them are below the age of 60, and you have one person who's 93. Well, you're not going to want to continue 65 to 75, 75 to 85, 85 to 95, just so that we find a way to get that last person in there. You're going to have a whole lot of intervals that have zeros in them just for the sake of the one. There's a point where it's futile. So what is often the case is for the last group, we kind of allow ourselves a larger area to capture. So you might say, well, the last group is 65 and above. It's all retirees, so we'll just do 65 and above, and you might set the upper limit to any number you want, 95, 100, it doesn't matter as long as it captures the last number. That's not that uncommon. On the lower end, you might do the same thing. Let's suppose I was doing ages of students in a university. Well, generally speaking, you don't see anyone below the age of 17. So I might say I'm going to start my lower limit at 17 for the first interval. So I might do 17 to 20 and then do 20 to 25, 25 to 30, 30 to 35, and so on. But for that first interval, there's no point in dropping down to 15 since freshmen don't go much below 17 very often. If they did, I would adjust accordingly. So you might find reasons, as I said, to make an adjustment at the low end and at the high end. But in the middle, I try to be as consistent as possible. If you abuse that, you can find all kinds of distortions. Like try to imagine, for example, if on this particular frequency table, I made the first interval go from 1.5 to 1.6. Well, it would only capture one person. And I could purposely make the next interval to go from like 1.6 to 1.8 or something like that and capture two people. And I can continue this pattern. So it looks like my histogram is going from 1 to 2 to 4 to 5, whatever, and all of a sudden it just blows up. And my last bar, let's say, goes from 2.5 to 4.0 and has 13 people in it. I'm all over the place, different sizes, but I don't care. When you look at the picture, it looks so stacked toward the end, and if anybody looks at the picture but doesn't look at the scales, they would say, oh my God, this school's giving away grades, grade inflation. What do they give you an A as soon as you walk in the door? But if you're looking at the actual scales, you'd see that last one had a really wide range to it, and the first one had a really narrow range. Unfortunately, most people don't read the scales. They just look at the pictures and jump to conclusions. So I could paint that image. I can go the opposite direction, make the very first interval ridiculously wide and say the first interval goes from 1.5 to 3.0. Well, that'll get 18 people right off the bat. And then make the next one capture only 3 or 4, then couple, then 1, and all of a sudden it'll look like, my God, this school just tries to fail everybody, don't they? So if you are messing with the sizes of the interval and don't try to, exhibit some statistical purity or ethics about how you do things, you could certainly paint a false picture, and you can intentionally do so. And believe it or not, it happens more often than you think when you look at pictographs in newspapers or what a lot of politicians try to throw at you. They're not exactly lying because they do have scales which accurately are telling you what belongs in that group. But since they know most people kind of look past the scales and look only at the graphs, and they're going to jump to the conclusions, they're getting what they want out of you. They're getting you to draw the conclusion from the graph without really paying attention to the truth. And to me, that's pretty tragic. So I'd rather people are more honest about how they display their data so that we can all get a much more accurate interpretation of what the results truly are. Frequency distributions are a wonderful way to organize the data, to basically put this massive data set that's totally disorganized into buckets, groups, whatever, and then to begin to make sense of it. It really does help, because if you just saw hundreds and hundreds of observations in front of you, you wouldn't know where to begin. So that's a good first step to making sense of the data. We can also go a step further in describing the data by running what we call descriptive statistics. If you look in this Excel file, which I call descriptive statistics, on the left side you can load a couple hundred observations, and then on the right side in those blue boxes, automatically all these statistics are calculated for you. Now all you're left to do is to figure out, what do they tell you? What does it really mean? Let's start with the first box, the measures of central tendency. Well, central tendency is basically a measure of location. Where is the data basically centered around? If somebody asked, how much does it cost to stay in a hotel in downtown Nashville? And you know the prices are all over the place, and you said, about $150. That $150 is kind of giving an idea of a central point to work from. They go, in their mind, they're going, okay, I know it's not super cheap, but I know it's not, ridiculously expensive either. I get an idea of what I could expect to pay. Even though it's just one number, it gives me a starting point. So central tendency is just that. It's that starting point of that location, so I know ballpark what I'm looking at. And you might use that expression a lot when I say, give me an estimate on how much it's going to cost to lay down wood flooring in my house, and they go, well, I need to see it first, and you're like, I just want to know an idea, ballpark, assume 2,000 square foot house, give me an idea. You want to know whether you're looking at something in the couple of thousand range or 10,000 plus range. I don't want them coming over and getting, wasting their time giving me an estimate when it's so far out of my price range that it's pointless, and it's wasting their time, my time, and we look under measures of central tendency, and we see 4 statistics mentioned there. Mean, median, mode, and mid-range. Now the little red triangles do describe these, but let me expand on these further. You will notice that they all begin with the letter M. There's actually one other one which is very rarely used called mid-quartile, but also begins with the letter M. So let's start with the mean. Now you may know the mean by its more common name, average. Okay, that's what the mean basically is. You've grown up with it all your life. You might think that it's some crazy statistic, but it's funny, when it's called a mean, people go, what is that? What is that? And you say it's an average, and everybody seems to understand it because you figure out your grades in all your courses, you're computing an average. If you watch sports, you see all the statistics on all these players. They compute batting averages and average yards per game and so on and so forth. So averages are very, very common. But here we call it a mean. Okay. It basically computed is just add up all the data, divide by the sample size. So whatever number of data, whatever the different observations are, add them up, divide by how many observations. So yes, it's a very, very simple statistic to compute. The symbol for it, if we're dealing with a population, it's a Greek letter mu. It looks like a U with a tail on the front. If you're dealing with a sample, then the symbol for it is an X with a line over it, and it's just called X bar simply. Now, the mean is a wonderful statistic because it uses all of the data. Nothing is left out when we calculate a mean. You can't arbitrarily decide what goes and what doesn't go. But one of the drawbacks of the mean, which is a very real problem, is the outliers. Any one extremely large or extremely small number can throw off the value of the mean, quite a bit. And we see that happen a lot in our society when we hear about what the mean or average income is or something like that amongst a population. One billionaire can make a population seem a lot wealthier. And you'd think that, can they really do that? But yeah, just think of Bentonville, Arkansas, for example. Here's a town of probably 1,000 people. And the most popular residents of that town are the Walton family, the very people whose family own the Walmarts. So Sam Walton and his kin. If you have a town of about 1,000 people in which you have, let's say, 3 billionaires amongst them, on average, this place looks like the land of plenty, where the average income of a person living there, seriously, could be over $1 million. You could have 99% of the people on welfare, 3 billionaires, and it looks like on average the people there make over $1 million. So clearly it's a case of outliers. When you have a really small sample, one very large number can really throw it off. So just be on the lookout for that. But as I said, the good thing is it does use all the data, which will become a really important advantage. The median is essentially the middle value in the data set. And in order to compute the median, the data must be sorted. So sorted from lowest to highest or highest to lowest, it doesn't really matter. Once the data is sorted, go to the physical center. So if I had, for example, 7 values, 7 observations, even if some of them were repeated, it doesn't matter. You sort the numbers from lowest to highest or highest to lowest, and the 4th position up or down is the median. Regardless of ties, it doesn't matter. The 4th position then would be the median because it's the physical center. If there's an even number, the method is to just take the average of the middle 2 values. So if I had 10 data points, for example, I would take the average of the 5th and the 6th after the data was sorted. So doesn't matter, odd or even, we have a way to compute it. What the median tells us, which is really valuable, is that half of all the data is above that point and half of all the data is below that point, which is quite useful. So if I go back to Bentonville, Arkansas, let's suppose that 99% of the population there is really making $20,000-ish salaries, let's say, and there's those 3 billionaires that live there. The median of $20,000 tells me, half the people are making above that, half the people are making below that. While the mean of $1 million makes it look, like I said, like, my God, I can get rich if I were to live there. So the outliers do not affect the median since it's the physical center. I don't care that there's a billionaire in the group. All that matters is that of the 1,000 people, the 500th person makes this amount. So outliers have no impact on them. Great statistic overall for that reason. Drawback to the median is you cannot draw inferences about a population. See, with a mean you can. Whatever you get for a mean from a sample, you can infer that to be the mean for the whole population. It doesn't work that way with a median because unfortunately when you're leaving data out, it's too great a chance that you've left out some of the higher and lower numbers, and the median cannot account for what is missing. So it's really wonderful for describing a sample, not so good for drawing inferences. So they both have advantages and disadvantages. I have a cartoon I love to show, which has got these 5 basketball players, 4 that are relatively short and 1 super tall. And on the bottom, the caption reads, "Shall we scare the opposition by announcing our mean height, or lull the opposition by announcing our median height?" And if you understand the two concepts, that would make a lot of sense to you. Of course, basketball, they're pretty obsessed with height as being the most important statistic that they report anyway. But that 1 single tall player makes the mean height go up. But when we do the median height, one of the short people will actually be the median person when we actually go to the physical center. So it really does illustrate the concepts quite well. The third measure of central tendency is the mode, which is nothing more than the most commonly occurring value. Whatever it is, the one that's repeated the most often is the mode. But you're not going to use the mode for something like a person's height or weight or age or income because you're not likely to see any repetition. If any, you might find 1 or 2 that are repeated, but it's rare. So it doesn't do us a lot of good to have something where you might have a repetition of 1 or 2 that doesn't really capture anything important. But for something categorical in nature, works really well. So you could have the mode for gender, the mode for hair color, and so on. It works fine for that. It's the most common group. And as I said, it would work fine for numbers that have a lot of repetition. So I could ask, what's the mode number of children that are in a subdivision? That would make a lot of sense, since everybody's pretty much got 0, 1, 2, or 3, and then the occasional more than 3. But if 95, 99% of the people are 0s, 1s, 2s, and 3s, perfect example of when a mode fits. The last one is midrange. The midrange truly is not used very often. It is the middle of the range. It is merely the average of the largest number and the smallest number in the data set. Well, the problem is that really large number or really small number could be an outlier, and the mid-range is still going to go smack dab between them all. So when we go to Bentonville again, if we have the lowest income person is making, let's say, $10,000 a year, and then you have a billionaire averaged into that, well, then the mid-range is $5 billion and 5,000. Because the mid-range is only using the extreme largest and the extreme smallest, giving each one half the weight. Well, when you have outliers galore, that's not a good statistic to use. So why use it at all? Well, sometimes it's appropriate because, well, I can think of two good reasons. One is get a quick and dirty answer. If I had a large data set in front of me, like those GPAs, and you notice that the largest GPA in the data set was 3.9 and the smallest GPA in the data set was 1.5, and they're all over the place, the median of those two numbers, the middle of those two numbers, if I averaged 3.9 and 1.5, I get 2.7. So basically I'm computing a mid-range. I average the highest and the lowest numbers and get a 2.7. If I don't want to go through the trouble of typing all the numbers in and doing a lot of number crunching, I can quickly come to the what the mid-range is, and that might give me a ballpark idea of where the median falls even. So it's just a quick and dirty measure of central tendency. The only other time I would use it is if I have no choice. If you're applying for a job which says this job pays $40,000 to $60,000, in your mind you're thinking, well, I'm probably going to make about $50,000 because you're thinking the midpoint of those values. You don't know if they're going to start you at the bottom. But so in your mind, you'll typically go after whatever the middle value is because all you have to work with is the high and the low. So either out of necessity or because you really want a quick and dirty answer, you would use the mid-range. Beyond that, you're not likely to use it. So we've got the measures of central tendency addressed. But there's really one more piece of the pie that we have to cover. If you wanted to truly describe any set of data, you need two pieces of information. You need a measure of central tendency and a measure of dispersion. One without the other is absolutely pointless. I mean, to just say that on average a salary is $1 million, you'd be going, my God, that's a lot of money. Well, it would be one thing if everybody was making $1 million or close to it. It's another thing when there's a two or three making billions and everybody else is making next to nothing. Two completely different pictures with the same exact measure of central tendency. So if you don't know what the spread of the data looks like, you really don't know what the data looks like. So you need two pieces of information. The central tendency measures, which we covered, and a measure of dispersion, which is basically the spread of the data. I like to think of this also as how big is the about. Going back to that, how much does the hotel cost? If I say about $150, the about is the give or take. Do you mean 150 give or take $10? 150 give or take $50? So that's the about that I'm talking about. That measures the dispersion of the data. And we have several different statistics which capture dispersion. The simplest one is the range. Now we think of range, what is the low and what is the high, and personally I prefer that a person tells me that. I'd rather you tell me the minimum and the maximum. If you tell me GPAs range from 1.5 to 4.0, that tells me a heck of a lot more than 4.0 minus 1.5 equals 2.5. But the statistic called range is just what the difference is between the high and the low, not reporting what it ranges from. So just so you understand the difference, like I said, personally I'd rather you tell me the minimum and tell me the maximum and let me do my own math because I know a lot more information, but the range itself is how wide is that distance. The standard deviation, well, this one can get quite ugly. The symbol for the standard deviation is the Greek letter sigma, which looks like a 6 that kind of collapsed for being too top-heavy, so you'll notice the tail of it's to the right. For a sample, the symbol for standard deviation is the letter S. Well, the standard deviation, if I show you the formula here, you see it can get quite ugly. Summation of x minus x bar squared over n minus 1 with a square root around it. And you go, my God, what is all that? Well, it's really the weighted distance around the mean averaged together. and then we take a square root. So what am I really doing here? Well, if I have some really large numbers, some really small numbers, and I want to know how spread out the data truly is, the simplest way to figure out how spread out the data is from each other is to say, let's start with one central point, the average. And then I say, well, how far above or below the average is each number? Now I've got, well, some are below and some are above. That's great. Now I analyze those numbers. Well, I know there's some that are always above the mean and some that are always below the mean. It has to be. If all the numbers were above the mean, it wouldn't be the mean, because the mean is in the center somewhere. It's not at the bottom and it's not at the top. So something has to be above and something has to be below. But if I analyze the how far above and how far below everything is, throw them all together, and let's suppose I averaged them. Let's just take a really simplistic example. Say the numbers 1, 2, and 6. The average of those three numbers is 3. 1 plus 2 plus 6 is 9, divided by 3 is 3. Well, the number 1 is 2 points below average. The number 2 is 1 point below average. The number 6 is 3 points above average. So we got a minus 2, a minus 1, and a plus 3. Okay, we now know how far above and below average everything is. Let's add those up. Minus 1 and minus 2 and plus 3, add them up and you get 0. Yep. So the average distance is the average spread then becomes 0, which unfortunately that's going to be the case, because that's what a mean really is. It's that perfect center of the data where if you add up all the distances of all the numbers above and below and then average them together, you're always going to get 0. It's a balancing point in the data. So what good is it? How can we truly measure the spread? Well, what we do in the formula is we square the distances. So if something is 2 points below average, we square that and make it a 4. If something is 3 points above average, we square that and make it a 9. That serves a couple of purposes. For one thing, it actually gets rid of the negatives. So now we have only positives, because the negatives and the positives were canceling each other out. So we got rid of those negatives, and now we actually are going to have something other than 0 for an answer. The other thing it does is it gives more weight to that which is further away. Well, 3 is further away than 2, which is further away than 1. Well, 3 squared is 9, 2 squared is 4, 1 squared is 1. So as you get further away, you square it, it really blows up. So we're going to add those up, basically average them, and then take the square root. The square root is kind of to undo the square that was already taken. So in the end, what are we getting? We're getting the average weighted distance around the mean. That's basically what a standard deviation is. And it has a lot of value to us. I mean, by itself, you look at it and go, what the heck does this tell me? I got a standard deviation of 5.28. What does that mean? And it's understandable, because by itself, it's useless information. Just like the mean by itself is not really valuable. You want the combination. And the mean paired together with the standard deviation is very, very powerful information. Because if you take a look at the bottom right, the lower right box on the descriptive statistics output, you will see it says mean plus minus 1 standard deviation, mean plus minus 2 standard deviation, and so on. And it gives a lower and upper limit. So like in the data set that's displayed here, we see a mean of 16.90 and a standard deviation of 11.29. Well, if I took that mean, subtracted a standard deviation from it, 16.9 minus 11.29, I get 5.61. If I add the two together, I get 28.19. So my mean plus or minus 1 standard deviation is that range. Well, it turns out that if I calculated how many of the observations fall between those two numbers, I get 13 in this case. The next group says mean plus or minus 2 standard deviations. So if I subtract 2 standard deviations and add 2 standard deviations, I get negative 5.69 and positive 39.49. Of the 20 numbers, 19 fall in that range. And then if I try it for 3 standard deviations, you see the numbers there, and all 20 fall in that range. Well, here's the interesting thing. If you take a data set, generally we want it to be something called normally distributed, which we'll discuss in the next unit. But what you'll find with almost any data set is if I take the mean and I add and subtract 1 standard deviation, According to something called Chebyshev's theorem, you have a certain expectation of how much data will be in that range. We expect roughly 2/3 of the data to fall into the range of plus or minus 1 standard deviation from the mean. It's really supposed to be close to that. When the samples are larger and they're nice bell-shaped data, you'll expect it to look like that. I wouldn't expect that kind of accuracy with smaller data sets. But nonetheless, we expect about 2/3 of the data to be within 1 standard deviation of the mean. Well, you'll notice 13 of the 20 in this case were within 1 standard deviation, which is 65%. If I go plus or minus 2 full standard deviations from the mean, we expect about 95% to be in that range. Well, it turns out 19 of our 20 happen to be in that range, which is 95%. Yes, it's coincidental. I expected to be in the ballpark. That was better than I could have expected. The third range, plus or minus 3 standard deviations, I expect to see virtually 100%. Officially, it's supposed to be like 99.7%, so I'm expecting it to be close to 100%. Turns out all 20 in this case were in that range. The standard deviation enables us to do this. Once we have the mean and the standard deviation together, we could say X% should be in this range, below this range, above this range, and so on. We can start to do that because it gives us such great insight into the data that we never would have gotten independently with just one statistic or the other. The two of them together tell us so much valuable information. So I like the standard deviation for that. But by itself, you're not going to look at it and go, wow, 11.29, gee, is that big? Now, one thing I would also note is that if you had to guesstimate a standard deviation, what you'll find is the standard deviation is typically about 1/4 the size of the range when you're dealing with small data sets, and typically about 1/6 the size of the range when you're dealing with larger data sets. So in this case, we have a small data set of only about 20, and the range is 39 points, so 1/4 of that puts us right around 9.75. So, it's in that ballpark. Whereas if we had a really large data set, 200, 300, etc., you would find whatever the range is. If you divided it by 6, you'd probably get a ballpark idea. Not great, because outliers screw it up, but you get a ballpark idea of the standard deviation. And the standard deviation is larger because of that spread. So if all the numbers were clumped together in the middle, the standard deviation would be closer to 0. If all the numbers are spread out, it's going to get bigger. Third statistic shown there is something called variance. Variance is pretty much the most useless statistic you will ever find in a stats book. Why it's there is still beyond me. But it's there nonetheless. And this is not the variance you'll hear about in a finance class where they're looking at actuals minus budgeted expenses, or in accounting classes or wherever else. This is a statistical variance. Basically, it is the standard deviation squared. The symbol for it is sigma squared, or S squared if it's from a sample. And it really doesn't tell us much as far as I'm concerned, because the problem I have with it is the units. While a standard deviation is in the units of the data, the variance is not. So if I had a case where I'm looking at, let's say, people's weights, and the mean weight was 150 pounds, and the standard deviation of the weights were, say, 8 pounds, the variance in that case would be 64. But 64 what? Square pounds? What's a square pound? Makes absolutely no sense. Neither does square dollars, neither does square degrees. So taking a square of a unit that should never be squared, it doesn't really do much for us. But nonetheless, they report it. So what the stats textbooks often do is when it comes to the variance, they just casually leave the units off. Which, if you cannot display the units for a specific value or variable, you got no business displaying that statistic. So I have a real problem with it, and I never would ask for anybody to give me the variance. So the mean and the standard deviation, they go really well together. Variance is really just an intermediate calculation, just the standard deviation squared, and that's about as far as I would go with it. The interquartile range requires that we cover one other topic first. If you go down to the other measures, well, sample size is pretty obvious. Minimum and maximum are pretty obvious. But then we have something called the first and third quartile. Now, if you take your data set and sort it and then you slice the data right in the middle. The point in the middle where you sliced it is the median. Half the data is above the median, half the data is below the median. So if you take the median of the lower half and the median of the upper half, you've divided it up into 4 equal quarters. Well, the median of the lower half is also known as the lower quartile or first quartile. The median of the upper half is known as the third quartile or the upper quartile. The thing about it is it's separating out 25% of the data from the rest. So the median says half are above or half, and half are below. The first quartile tells us 25% are below this point. The third quartile is telling us 25% are above that point and 75% are below that point. So it's telling us information just like the median did, except it's actually giving us a little more insight into the spread of the data, since we've already broken our data up into 2 groups and it's telling us how far out we go before we're at the halfway point again. Now think about the value of that. If you look at this data set, the third quartile is 25. Well, the mean is 16. The high goes all the way up to 40, but the third quartile is only 25. That means 25% of the data is somewhere between 16.9 and 25, and 25% is above 25. I've seen that many times where the first and third quartile are really, really close to the median, and then the minimum and maximum are way, way out there. A lot of times I'll see them when grading exams in a class. You might have the class average was 80, and the high might have been 100. The low might have been 2, but the median was, let's say, 80. And then if I went to the first and third quartile, I might see, let's say, 72 and 87. That's telling me half the class got between 72 and 87. 25% were above 87, 25% were below 72, and it dropped all the way down to 2. So it also says I'm not dealing with outliers, because if I'm throwing out the top 25% and the bottom 25% to calculate this, the outliers are not going to be a problem. So anyway, that's how we get the first and the third quartile. The interquartile range, which shows up on the measure of dispersion, is just the distance between those two numbers. The range tells us how far the minimum and maximum are from each other. 1 and 40 are 39 apart. The interquartile range says how far are the two quartiles from each other. In this case, 7 and 25 are 18 apart. So you have an idea how spread out the middle piece of data actually is. And lastly, on that chart, it shows the coefficient of variation. Well, that in and of itself is telling us how big is big. If I were to tell you the spread of my data, well, the standard deviation happens to be 11.29, you might go, is that a lot? I don't know. Well, the way I can tell if it's a lot is I divide it by the mean. Because, well, try to think, let's suppose we're looking at people's salaries. If I said the standard deviation for the salaries in a specific organization happens to be, well, let's say $1 million. Is that a lot of money? Well, to many of us, yeah. If the spread is $1 million, my God, that's a monstrous spread from what we could see. But if I told you, oh yeah, the organization I was dealing with, Tennessee Titans. Oh, so you're dealing with salaries of $10 million, $15 million, $30 million, $1 million. Oh, I'm dropping the bucket. My God, what are you paying them all the same? All of a sudden, that $1 million doesn't sound like a big spread. Not when we're dealing with salaries of $10 million and above. So relatively speaking, it may be a lot. It might be that $10,000 is a hell of a lot, and $1 million is not that much. The way you tell is take the standard deviation and divide it by the mean. So in this case, 11.9 divided by 16.90 happens to be 66.83%. It gives us a better idea of, is it a big spread? If I were to ask everyone if I were to point out an object and say, how large is this object? Write it down. And then I reported the results, and I said, oh, the standard deviation of all your guesses happens to be 6 inches. I'm like, is that a lot? Well, the answer, it depends. Statistics does mean never having to say you're certain, and boy, is that the case here too. Is 6 inches a lot? Well, if I were asking you how large is my pen, 6 inches for a standard deviation is monstrous. That means that easily the distance between the lowest number that I got from any of you and the highest number I got from any of you is probably about 2 feet or so. That's a big spread for a pen that's like 4 or 5 inches long. On the other hand, if I asked y'all, how large is the room I'm standing in? And the room I'm in might be 40, 50 feet long. Now, if the standard deviation is 6 inches, you'd go, my God, y'all must have guessed about the same, didn't you? It's amazing how 6 inches could look so monstrous and yet so small. And it's all relative. One last statistic here, percentiles. Percentile tells me what percent falls below a certain number. So the median we actually know is the 50th percentile, since 50% of the data falls below the median. We know the third quartile is the 75th percentile, since 75% fall below it, and the first quartile is the 25th percentile. But what about the rest? You might say, well, I'd like to know where the top 10% happens to be cut off at. I want to know where the bottom 10% happens to be cut off at. So, if you plug in the 90th percentile, you're going to find out the point at which 90% are below, and 10% are obviously above. In this particular case, it showed a 90th percentile of 32.1. They have to do estimates, approximations, or whatever whenever the data set is small. If you have hundreds of data points, the 90th percentile will physically find a data point at which the 90% fall. But when you only have 20, we have to kind of project upward to a larger data set. So that's why you might see a fraction and be somewhere between a couple of numbers. It's basically interpolation. So here it's telling us that a value of 32.1 is the 90th percentile, because 90% of the data is below that number. And yeah, you'll notice that 18 of the 20 data points are 32 and below. So it does work quite well. Back in New York City, we did standardized testing every single year. And I know every state still does something like this, but in New York State, 1 week out of every school year, we would take a series of tests for a couple hours a day, math, English, science, whatever. And then a couple of weeks, few weeks later, whatever, we'd get a report back which showed our scores. The report didn't actually have your raw score. It gave your percentile. So it said, 99, meaning that you beat 99% of the people who took that particular test. 99% of the scores were lower than yours. Now, I noticed a couple of things, because I was always into this stuff. Anyway, even as a kid, I noticed that the boxes that were used to display the percentiles only had room for 2 digits. So I kind of wondered. I had a 99 on math, a 99 on science, let's say 95 on English, 85 on this, or whatever. But I always had a 99 on math. Year after year after year, I had 99 on math, and I noticed there was no room for 100. Well, being the inquisitive kid, my teacher was a nun at the time in grade school, and I asked Sister, why is it that the scores are rigged so that you never have 100? I noticed that I got a 99 here, and there's no room to put a third digit in there. And she gave the one pat answer that seemed to work really well for a nun teaching a 10-year-old. She said, because only God is perfect. Well, that pretty well shut me up, and who am I to argue with that one? I'm like, oh, okay, so 99 is about as good as I'm going to get. Well, that's not the correct answer, not questioning the perfection. I'm talking about the percentile. The reason why you won't see a 100 is because a 100th percentile is impossible. For you to be on the 100th percentile means you scored higher than 100% of the people who took it. The problem is you are in the group, and you cannot possibly score better than 100% if you are part of the group, because that would mean you scored better than yourself, which is impossible. So you can only score better than all but you, which means by default 99%. So that's why percentiles stop as high as 99. They could go down to 0. You could beat absolutely no one, but you cannot possibly beat 100%. So yes, percentiles range anywhere from 0 to 99. So next time if you see that, don't think it's your score. It doesn't mean the percent you got right. It's the percent of people that you scored better than. And they do percentiles for other things too. When you have a small child, the doctors will report the percentile your child falls into with heights and weights and stuff like that. That's the percentage of children he weighs more than or less than. And it doesn't mean your kid is abnormal or sick or something. It just gives you an idea of his rate of growth, where he fits into the rest of the population. So it's a very, very popular statistic. So that wraps up all the descriptive statistics. You now have seen them all in action, and from that, from what we've gathered today, you can see how you can take a set of raw data, and if it's categorical or at the very least discrete, do some categorical analysis. If it's continuous, you can do the frequency distributions. And then if it's any numerical data that's quantitative in nature, you could certainly do the descriptive statistics and then try to make sense out of what you see there. And some people choose to focus on certain statistics over others. Based on what you like to focus on, you can draw all kinds of conclusions, and it's always interesting to see the kinds of conclusions I get. But one thing for sure, make sure your conclusions are grounded in the data. Well, this completes Unit 1. In Unit 2, we'll be delving into the world of probability.